Okay, good evening, everyone. Let's start with our discussion. So we shall carry forward the slab discussion this week. Hopefully, this will be the last week for slab. Thereafter, we will go for columns. So let us carry forward the discussion. Especially, we will mainly today for this discussion. Will this week we will mainly focus on the two-way slabs, right? So let us go to the 6 week lectures. Okay. So let us take a problem. Okay, uh, let us design a simply supported two-way slab with UDL. Okay, that is a reinforced concrete slab which is having a dimension of 5.5 meter by 4 meter. Okay, and it is simply supported on all the four sides. Okay, and it has to carry a characteristic live load of 8 kilonewton per meter square. The concrete can be taken as M25 grade. The steel can be taken as Fe415 grade, and the exposure condition to environment is mild. Okay, so for this for mild condition, we all know the clear cover will be 15 mm, otherwise it will be taken as 20 mm. Okay? So let us see how to solve it. So let us assume that the span by overall depth ratio is 30. Okay, uh, it should be less than 35. Okay, as per the this one IS code. Okay, so for two-way slab case, if it is simply supported, it should be less than 35, and for continuous it should be 40. Okay, this condition is little different than the actual condition. Okay, so that was, I think, 7, 20, and 25, 26. So cantilever it was 7, simply supported it was 20, and continuous beam it was 26, right? So that was for the general case. Okay, but for two-way slab, okay, for two-way slab up till 4 meter, we can take this condition. Okay, so span by overall depth 30. Okay, so that is mentioned in IS code. There are some conditions. Okay, and also if we multiply the modification factor, it will definitely be higher than this one. So we will check that also later on. So let us start. So let us assume span by overall depth as 30. Okay, and because the grade is Fe415, that is HYSD. So as per IS 456 clause only, so it will be multiplied by zero point 0.8. Okay, so 30 into zero point 0.8, which is 24. Okay, so that is the allowable. Okay, and L by, so definitely it should be less than 35 into 0 0.8, that is around 28, right? So if it should be less, so uh, if we have taken less only, so it will be definitely be lesser, right? So it is, we have to find whether it is satisfying. So taking L by D as 24, L we all know the shorter side, it is 4 meter. So D will be equal to L by 24, that is 4000 by 24, right? So that will come up as 166.66 millimeter, or 166 millimeter simply. So rounding this figure, let us take overall depth as 175 millimeter. Okay, so more we take, it will be definitely less than 24, right? So it is better. So as I told you, because of the mild condition, okay, so we can assume clear cover is 55 mm, and 10 mm diameter. Or because nothing has been given, let us assume the diameter bars of the rebars are 10 millimeter. Okay, so D provided, the total the actual depth provided is 175 mm. So effective depth will be 175 minus 15 minus half of 10, which comes out to be 155 millimeter. Okay, so now let us calculate the design load. Okay, so for the design load, we have to consider dead load and live load. Okay, so dead load basically will come from slab, floor, and plastering. Okay, so slab, uh, yeah, so slab, the effective depth is 0. Sorry, the total depth is 0.175 mm. Okay, so 0.175, and we are taking everything per unit width. Okay, so it will be multiplied by 1. We are taking width as 1 meter. Okay, and as we all know, RCC, the density is 25 kilonewton per meter cube, and for plain concrete it is 24 kilonewton per meter cube. Okay, so floor finish we are assuming as 25 millimeter thickness, and plastering as 6 millimeter thickness. So this will be 0.025, and this is 0.006, right? So the slab dead load therefore will be 0.175 into 1 into 25, that is 4.375 kilonewton per meter. Similarly, floor finish will be 0.025 into 1 into 24, which comes out to be 0.6 kilonewton per meter, and plastering will be equal to 0.006 into 1 into 24, which comes out to be 0.144 kilonewton per meter. Okay, so adding all this three, we get a value of 5.119 kilonewton per meter, which is the dead load. Okay, and live load, I think it is mentioned. Yeah, so characteristic live load is 8 kilonewton per meter square. So taking that width as 1 meter, so it will be 8 into 1, right? So 8 into 1, that is 8 kilonewton per meter. Okay, so therefore the total load will be 8 plus 1 5.119, which comes out to be 13.119 kilonewton per meter, right? And taking the factored load, for finding the factored load, we have to just multiply this by the that is the partial safety factor. So we multiply it by 1.5. Okay, so we overestimate. Okay, so yeah, so multiplying 1.5 into with 13.119, we get it as 15 into this one, 15 into 13.119. So sorry, I should multiply it here also by 1.5. So it should be 1.5 into 13.119 kilonewton per meter, which comes to be 19.6785 kilonewton per meter, right? So yeah, so based on this, we can calculate the mx and my value. Okay, so for the two-way slab, right? So yeah, so mx will be, as we derived in the last class, mx will be alpha x w lx square and my will be alpha y w lx square. Okay, so w and lx square will be constant, right? W is 19.6785 kilonewton per meter, right? And lx will be 4 meter, right? Okay, and the alpha x will be calculate alpha x and alpha y, we will be calculating using the table 27. Okay, using the table 27, page 91, IS 456 2000. Okay, so I think we will have to we will be using I think the ly by lx. Yeah, we have to find the ly by lx ratio. Okay, so that is 5.5 by 4. Okay, ly is 5.5, lx is 4, so 5.5 by 4, that value. Okay, so corresponding to that value, we will get alpha x and alpha y from this table. Okay, so for alpha, based on that, alpha x comes to be 0.0975 and alpha y comes to be 0.052. Okay, so yeah, so therefore, putting the values in the respective variables, we get mx value as 30.69846 kilonewton meter and my as 16.372512 kilonewton per kilonewton meter. Okay, so so now let us check whether the depth is as per require, like whether the given depth is satisfying the required depth. Okay, so yeah, so the maximum moment is 30.69846, right? So taking this as a limiting moment, we know for fe415 the limiting moment equation is mx equal to 0.13 at fck bd square, right? So fck is 25 megapascal, b is we have taken per unit width, so it will be 1 meter or 1000 millimeter. So let us find the d. Okay, so d comes out to be, substituting the values, the value of d comes to be 94.329 millimeter. Okay, however, we have provided 155 millimeter, so definitely 155 is greater than 94.329. Okay, so our given depth is satisfied. Okay, now let us check the areas of steel. Okay, so for that we will be using the x by d value. Okay, x by d ratio. So we already know x by d is equal to 1.2 minus square root of 1.2 whole square minus 6.6 mu by fck bd square. So we have done this in the last classes. Okay, we have derived this. So x by d value will be this formula. Okay, so 6.6 mu by fck bd square will be 6.6 into 30.69846 into 10 to the power 6 by 25 into 1000 into 155 square, right? So this comes to be 0.3373316. Therefore, x by d will come to be 1.2 minus square root of 1.44 minus 0.3373316, which comes to be 0.15. Okay, and that is less than the limiting x by d ratio, which is 0.48 for Fe415 steel, right? So this condition is also satisfied. Okay, and this also means that the section will be under reinforced section. Okay, because it is less. Okay, so yeah, so the lever arm jet. Okay, so that will be equal to d into 1 minus 0.416 x by d, right? So that d is 155 and x by d is 0.15, right? So the lever arm jet will be equal to 155 into 1 minus 0.416 into 0.15, which comes to be 145.328 millimeter, right? and the area of steel, okay, in the shorter direction, because the main steel in this case of slab is in the shorter direction, okay, unlike the this one, unlike in the beam case, which is in the longer direction or longitudinal direction. Here it is in basically in the main steel is provided basically in the transverse direction, okay. That's why we take the unit width, okay. Width has 1 meter always, okay. So area of steel in the shorter direction, AST, will be mu by 0.87 FYZ. So this is similar to the beam criteria, right? So the formula is basically the same. So mu, as we all know, it came to be 30.69846 into 10 to the power 6, and Fy is 415 and Z is 145.328. So putting the values, we get AST value as 585 millimeter square, okay. So that is the area of steel in the shorter direction, right, in the transverse direction. Now let us see the area of steel in the longitudinal direction or the longer direction. So this is the 585 square. Sorry, this is the 585 square, the line, okay. So the line is the 585 square, and this is in the longer direction, the dots, okay, which we will be calculating now, okay. So area of steel in the longer direction. So here the effective depth in the larger side, it will be, so because it is placed above the transverse steel, right, so it will be 175 minus 15 minus 10 minus 10 by 2. So basically the rebars, the size of the rebars for both the shorter direction and longer direction have been provided basically the same, okay. But we can also change, we can reduce this to 8 also, okay. But it is good to give height, okay. So they have maintained the same, it's good. So effective depth in the larger side will be 175 minus 15 minus 10 minus 10 by 2, right. So solving this, we get to be with 15, 25, 30, okay. So 175 minus 30, which is 145, right. So 145 millimeter. So the lever arm Z will be D into 1 minus 0.416 x by D, right. So here x by D, they have again calculated using this equation, okay. So they have just substituted the values, right. So mu is the this value, I think 16, yeah, 16.372512, okay, because in the y direction. Then your yeah, so that is the 16 point something kilonewton meter. FCK is 25, B is 1000, and D is 155, right. Sorry, 145, right. So substituting all these values, we get Z is equal to x by D is 0.089, and Z is equal to 145 into 1 minus 0.416 into 0.089, okay. That basically comes to be 139.6 millimeter, okay, approx 140, right. So the AST value comes to be 16.37. Again same formula, AST equal to mu by 0.87 FYZ. So as I told you, mu is 16.372512 into 10 to the power 6, Fy is 415, Z is 139.6. So substituting the values, AST is 324.83 millimeter square. Though therefore the spacing required will be 1 meter or 1000 divided by 324.83, 1000 divided by the number of bars, okay. So number of bars is 324.83 divided by pi by 4 into 10 square, okay, which is 78.5, okay. So that is equal to 1000 into 78.5 by 324.83, which comes to be 241.66 millimeter, okay. So we shall provide 10 phi 10 diameters at the rate 240 center to center, okay. So if we follow this, the AST will be 327 millimeter square, which is greater than 324.83. So condition is satisfied. So here for this one, for the given case, the modification factor, if we see, okay, so that will come to be around 1.5, okay, as per the conditions which we discussed previously. And for P value equal to, so P is the area of steel, percentage of steel, so that for P equal to 0.3774%, Fs equal to 224 Newton per square. There was a formula 0.58 into Fy into area of steel provided by required, something like that formula was given, right. So using that, we calculate the Fs. So that is 224 Newton per square. So allowable L by D will be this is a general case, okay. So this is 20 into 1.5 by 30, okay. So yeah, so we took basically this condition, okay, assuming that the slab, because it is a two-way slab, we assume that it is as per the require satisfying the requirements. But if you see that formula, that clause, So there it is written that that is the L by D should be the span of depth, the span of the slab should be less than 3.5. Okay, but here it is 5.5 and 4 meters. So therefore, although we have taken that, but we have to satisfy the basic criteria, which is the this one for simply supported, it should be less than 20, right? It should be less than 20 generally, and by multiplying the modification factor, it should be less than 30, right? So allowable L by D is 20 into 1.5, which is 30, and which we have provided L by D, that is 4000 by 175, which is 22.85, or L by effective depth 4000 by 155, which is 25.80. Okay, even if we place 145 also, still it will be less than 30. Okay, so our condition is satisfied as per the clause 23.2.1. So this is basically the main clause. Okay, the other clause, which the 35 and 40 L by D ratio, that is mainly for two-way slab having span less than 3.5 meter, and I think load should be less than 3.5 kilonewton per meter square, something like that. But this is the general formula, so the criteria. So if we satisfy this, everything is okay. Okay, so based on this problem and based on the solution, we can summarize our design. So we can design the slab such that the overall depth is 175 millimeter, the clear cover is 15 millimeter. Okay, the reinforcement in the shorter side is 10 phi at the rate 125 millimeter center to center. Okay, the reinforcement in the longer direction is 10 phi at the rate 240 millimeter center to center. The concrete is M25, steel is Fe415, and yeah. So basically, these are the conditions. That is the spacing for spacing. We generally see that it should be lesser of the value calculated, right? And it should be lesser of the value calculated, 3D, and uh, one more was there. I think I forgot. I think it is 450 or 300 something like that. So I think it was 300, yeah. So it should be lesser than the calculated value 300 for 3D value, so which comes to be 435 So our conditions are satisfied if we take spacing of 125 and 240 millimeter, right? So yeah, so as per this, our conditions are satisfied, and the design is correct. Okay, it is satisfying all the conditions. So that's how we have to design. Okay, so yeah, so let us take one more problem. Okay, so here this is a this is a bay. Okay, 2 by 2 into 5, 2 by 5 bay. Okay, which is having 10 panels, right? So let us consider this panel. Okay, so here the shorter side, okay, which is basically continuous. Okay, so this is 4 meter. Okay, and the longer side is the 5 meter. So ly is 5 meter, lx is 4 meter. Okay, and here let us name this slab as b1 c1 c2 b2. Okay, so let us name this slab, or basically the panel, as B1, C1, C2, B2. So here concrete is having a grade of M20, steel is having a grade of Fe415, live load is 4 kilonewton per meter square, right? So yeah, so let us design for this slab. Okay, so how to design for this slab? So yeah, so assuming it is a mild exposure, so clear cover, let us take 15 Okay, let us assume 10 bars. So as I told you, Lx value is 4 meter, Ly value is 5 meter. So Ly by Lx is 5 by 4, which is 1.25. Okay, so now we have to find a load calculation. Okay, so basically for dead load calculation, initially we need to find out the or assume the depth. Okay, so let us assume the overall slab depth is 150 so this is generally a good value. Okay, so overall slab depth, if it is taken as 150 it is a good value. So if the d is 150 effective depth small d will be 150 minus 15 minus 10 by 2, right? So it will be 150 minus 20, or 130 millimeter. Okay, so the design load. Okay, so again we have considered this, for dead load we have considered slab, floor finish, and plaster. Okay, floor finish is 25 thick, plaster is 6 and both are plain concrete, right? And for slab it is reinforced concrete. So yeah, so 25 and 24 respectively. Okay, so it will be, and because it is we have considered unit width, so we multiply every value by 1. So it is 0.15 into 1 into 25, which comes to be 3.75 kilonewton per meter square. Actually it is kilonewton per meter. Okay, so similarly this will be 0.025 into 24, which is 0.6 kilonewton per meter, and this will be 0.006 into 24, which is 0.144 kilonewton per meter. Okay, so here it is written meter square, but if you multiply by 1 again, it will be kilonewton per meter. Okay, so dead load will come to be 4.494 kilonewton per meter square or meter, and live load will be 4 kilonewton per meter square. So it is mentioned. Okay, so again, if you multiply by 1, it will be 4 kilonewton per meter. Okay, so the design load will be how much? It will be one addition of this and multiply by 1.5. So it is 1.5 into 4.494 plus 4.0. Okay, which comes to be around this one 12.749 kilonewton per meter. Okay, so instead of writing meter square, they have just mentioned per unit width. Okay, so that is multiplying by 1 meter. Okay, so W value is 12.741 kilonewton per meter. Okay, so if we compare the panel with the various types of panels mentioned in table 26, okay, we find that the case 2 condition, okay, so that condition matches the this interior this panel basically. So that condition is one short edge continuous. So as I told you, this is a shorter edge because Lx is less, right? So this is continuous. So this is the one short edge continuous condition. Okay, so for that condition, and for Ly by Lx value of 1.25, okay, so our value for sagging and hogging, okay, hogging and sagging, so that will be the alpha x value, okay, negative and positive for shorter span and larger span. So larger span will be this one 0.037 and 0.028. For shorter span it will be between this because it is 1.25. Okay, so for 1.2 it is this, for 1.2 it is this, for 1.3 it is this. So our value will be middle. Okay, so if you if we try to interpolate for Ly by Lx equal to 1.25, the negative for alpha x, the negative value will be 0.0495. For alpha y it will be 0.037, and the positive value will be 0.0375 and 0.028. Okay, for alpha x and alpha y respectively. So again, using these equations for calculating the moment, mx equal to alpha x w lx square and my is alpha y w lx square. So shorter span support moment will be, that is the hogging moment. So that will be 0.0495, okay, into 12.741 into 4 square. Okay, that is 10.09 kilonewton meter. And span moment or the sagging moment, okay, so this is 0.0375 into 12.741 into 4 square, which is 7.6446 kilonewton meter. Okay, similarly for the larger span, okay, so the value will be the same because there is no effect of Ly by Lx ratio. Okay, so it is 0.037 and 0.028. So as you can see, 0.037 and 0.028, okay, into 12.741 into 4 square. Okay, so for support moment it will be 7.5426 kilonewton meter, and for span moment it will be 5.707 kilonewton meter, right? So if we compare all the values, we say that the maximum value is this, okay, 10.09 kilonewton meter. That is the support moment in the shorter span. So maximum moment is 10.09 kilonewton meter. So again, taking Fe415 Hy as the bar and using the limiting moment condition, mu equal to 0.13 FCK BD square. So B is 1000. Your FCK is 20. So yeah, 20 M20. Yeah, steel is Fe400. So FCK is 20, and B is 1000, M is 10.09 into 10 to the power 6. So we get D value as 60.46 millimeter. Okay, but we have taken the D value as how much? 130 mm, right? So our D value is more than the required D value. So the condition is satisfied. Okay, and x by D, again we using that formula 1.2 minus square root of 1.44 or 1.2 square minus 6.68 mu by FCK BD square. So again using this formula, we get x by d values as 0.087, which is less than 0.48. Okay, and it is under reinforced. Okay, so therefore z is equal to 130 into 1 minus 0.416 into 0.087, right? which comes to be 125.29 millimeter. Okay, and AST will therefore be mu by 0.87 FY z, right? So yeah, so putting the values 10.0, we get 10.09 into 10 to the power 6 by 0.87 into 415 into 125.29. That comes to be 223.05 mm square. Okay, and spacing required therefore, assuming that the bars are of 8 mm, okay, 8 mm dia. So yeah, 1 mm, 8 mm dia bar AST, yeah, area of stirrup will be 50, okay, 50 mm square. So spacing required will be 1000 by 223.05 divided by 50, which comes to be 224 mm. Okay, so spacing should be minimum of 224, 3 into this one, D, that is 130, which comes to be around to 390 and 300. So therefore it will be 224 only. And yeah, so it should be this should be the minimum. Okay, so it is even better to provide lesser. Okay, so let us provide 85 at the rate 200 mm center to center. So therefore SD value will be 250 mm square, which is greater than 223.05, right? So that is the AST we have provided. Also, this is also greater than this one. Also, the minimum criteria also we can check AST minimum. So if you see clause this one, if you see IS 456, for the case of slab, the minimum reinforcement for mile bars is yeah, it is 0.15% B into B into D. Okay, and for HYSD bars it is 0.12%. Okay, B into D. Okay, so B is 1000, D is 130, and 1.12%. So it is 0.12 by 100. So it comes to be 156 mm square, which is definitely less than both 223 and 200. Okay, sorry, 250. So 156 is less than 223 and 250, so our condition is satisfied. Okay, so therefore we will give detailing of the reinforcements like this. Okay, so these are the general criteria by which we give the detailing, and this has been quoted in SP 34 1987. So you can refer that for providing the reinforcements in a monolithically cast beam and slab respectively. So yeah, so you can refer that how to provide proper detailing, but this is the minimum requirement. Okay, so if we provide this, our conditions are satisfied and the beam is capable of taking the slab is capable of taking the required moments. Okay, so yeah, so with this we come to the end of the lecture part for this week. Okay, the last week basically it was a it was basically a finishing, I would say, finishing of the revision of the slab part. Okay, so it was a relatively smaller week. Okay, so let us now go to the solve problems. Okay, so yeah, so first question, match list 1 to list 2 with regard to the basic values of span to overall depth ratios of two-way solid slabs for shorter spans, okay, up to 3.5 meter, adhering to the vertical deflection limits for loading class up to 3 kilonewton per meter square, reinforced with HYSD bars. Okay, so list 1 type of slabs simply supported and continuous, and list to 7 to the values have been given 7, 28, 32, 35, 40. Okay, so which will be the correct match? Okay, so this condition I just told you in the beginning of this lecture, today's lecture. So yeah, so there is the L by D general, this one, L by D, that is basically spent by effective depth ratio, 7, 20 and 26 for cantilever, simply supported and continuous, this one case respectively, right? For two-way solid slabs also, apart from that, there is one more condition, as I told you, the span by overall depth. Okay, so that can be taken as if it is less than 35 and 40 for simply supported and continuous slabs, two-way slabs respectively. So we can say that our condition is satisfied. Okay, uh, also in that case, if we have use hy as the bars, then that values have to be multiplied by 0.8. Okay, so that 35 will become 35 into 0.8, which will be 28. Okay, so then if you are using HYSD, so it will be 28 and 40 will become 32. Okay, so 28 and 32. Okay, But for that, these two conditions will be there, should be there. That is, shorter span should be less than equal to 3.5 meter, and loading should be less than equal to 3 kilonewton per meter square. Then only that condition will be satisfied. If not, if these conditions are not there, then we have to take the general condition, that the 7, 20, and 26. Okay, and we have to add modification factor and other things. Okay, so for this case, it will be yeah, for simply supported it will be 28, that is a will be 2. Okay, so a is 2, and continuous it will be 32, so b is 32, so b is 3. Okay, a is 2, b is 3, which is d. So option d is the correct option. So hint is clause 24.1. Okay, notes point 2, page 39, IS 456 2000. And for, as I told you, for the HYSD bars, the overall depth to span ratio multiplied by 0.8, right? So D is the correct option, as I told you. So as you can see, D is the correct option. Okay, so A is 2 and B is 3. Okay, so next question, question number 2. Following are the details of an unrestrained reinforced concrete simply supported on all four walls. Okay, so yeah, so here the effective dimension is 4.5 meter by 6 meter. Thickness of the slab is 200 mm. It carries a characteristic live load of 10 kilonewton per meter square in addition to the dead load and finishing load of 1 kilonewton per meter square. Grade of concrete is M25. Grade of steel is Fe415. Clear cover of 20 millimeter. Bottom reinforcement is 12 millimeter diameter. Top reinforcement of 10 mm diameter at the midspan of the slab. Consider the following statements. 1. The slab carries a dead load of 5 kN per meter square. 2. The design load as per limit state method is 24 kN per meter square. 3. The slab is a two-way slab. 4. The effective depth along the shorter span is 174 millimeter. 5. The effective depth along the longer span is 125 millimeter. Okay. So which of the statements is or are incorrect? A 1 only, B 5 only, C 3 and 4, D 3 and 5. So let us check. Okay. So live load, as it has been given, is 10 kilonewton per meter square. Dead load is so it will be basically how much? Yeah, so it will be for this one, for slab it will be zero point 0.2 into 25. Okay, 200 mm. That's why 0.2 into 25, which is 5 kilonewton per meter square. And here, yeah, so here finishing is given but flooring is not given, so we don't have to add for flooring. Okay, so finishing it is 1 kilonewton per meter square. Okay, and yeah, so yeah, no flooring, so total dead load and live load combined it will be 15 plus 10 plus 5 plus 1, right? Yeah, so it is 10 plus 5 plus 1, which is 16. Okay, 16 is the total load and factored load will be 1.5 into 16, that is 24. Okay, kilonewton per meter per unit weight. Okay, so therefore, yeah, the dead load of 5 kilonewton per meter square is satisfied and design load of 24 is also satisfied. So both 1 and 2 are correct. Okay, so 1 and 2 is, so A is not correct. Okay, then Ly by Lx, if we see 6 by 3.4.5, so it will be definitely be less than 2. Okay, so it is around 1.33, so it is a two-way slab. Okay, so 3 is correct. Okay, so yeah, C is also, C and D are not correct. One is A is also not correct, so correct option is B. Okay, so let us see in the more detail. So yeah, along the shorter span the effective depth dx is how much? 200 minus 20 minus 12 by 2, right? So it is 200 minus 20 minus 12 by 2, which is 80 minus 6, that is 174, right? So it will be 174 mm, so it is correct, 174 mm. And the effective depth along the longer span, so longer span will be how much? 200 minus 20 minus 12 minus 10 by 2, right? So 200 minus 20 is 180, right? 180 minus 12 is 168, right? 168 minus 10 by 2. It will be how much? Uh, yeah, so it will be 168 minus 10 by 2 is 163, right? So this should be 163 mm, the effective depth along the longer span. Okay. So yeah, so 4 is correct, but dy should be 163 mm. So here, as it has been provided 125 mm, it is not correct. So B is the correct option. So which is incorrect? 5 only. Okay. So as you can see, B is the correct option. 5 only. Okay. Then third question. Following are the details of an unrestrained reinforced concrete simply supported on all four walls. A effective dimension for 4.5 meter by 6. So I think it is the same question. Okay, so the same question has been given, and we have to consider the following statements. One, the coefficients of moments along shorter span is 0.0948. Okay, the coefficients of second of the statement, the coefficients of moments along longer span is 0.085. Third statement, the maximum factored bending moment in the shorter span is 46.08 kilonewton meter. And fourth statement, the maximum factored bending moment in the longer span is 46.48 kilonewton meter. Okay, so we need to find out which of the statements are incorrect. Okay, so let us see. So as we have already calculated, total load is 16, okay, and factored load is 24, right? And it was a two-way slab, right? So using table 27, okay, and that is page 91, IS 456. So we get alpha x value as, by interpolation, it is 0.0948. So the first statement is correct. Okay, so A is correct. So A will not be the option. Okay. Second alpha y value is 0.0538. Okay, so this is wrong. Okay, so 2 will be incorrect. Okay, so 2 is will be an option. Okay, so it will be either B and C. Okay, then so D will not be an option. Okay, A and D will not be an option either. It will be between B and C. So yeah, then using the alpha x and alpha y value, we can calculate the mx and my value, right? So it will be alpha x w lx square. It will be alpha y w lx square. So w is 24, lx is 4.5, right? So yeah, so 0.0948 into 24 into 4.5 square is 46.08 kilonewton meter. So 3 is also correct. Okay, and that is not an option also, not, but the option is not provided for 3. So yeah, so this is correct. And fourth, it will be 0.0538 into 24 into 4.5 square, which is 26.15 kilonewton meter, but here it is 46.48. So this is also incorrect. So 2 and 4 both are incorrect. Okay, so we can say that C is the correct option. Okay, C is the correct option. Okay, so as you can see, C, that is 2 and 4 are incorrect, is the correct option. Okay, fourth question. A simply supported reinforced concrete slab of effective dimension 4.5 meter by 6 meter is carrying a uniformly distributed load of 16 kilonewton per meter square, inclusive of the dead load, live load, and floor finish. Assuming M25 grade of concrete and Fe415 grade of steel and thickness of the slab being 200 mm and 20 mm cover, what is the required area of steel in the shorter span if 12 millimeter bars being used? Okay, so what is the required area of steel? Okay, so is it 793.65 mm square, which is it 526 mm square, is it 967.6 mm square, or is it 1056 mm square? Okay, so let us check. So the factored design load will be yeah, so getting a uniformly UDL value 16, right? Which is inclusive of dead load, live load, and floor finish. So this is the given load. Okay. So factored load will be 1.5 times 16, which is 24. Okay. And D value effective that will be how much? So thickness is 200, right? So clear cover is 20, and yeah, so in the shorter span, we are providing the diameters, we are reinforcement first, okay? So that will be the bottom reinforcement itself. So it will be effective, that will be 200 minus 20 minus 12 by 2. That is 180 minus 12 by 2 or 174, okay? So 174 mm. And Ly by Lx value will be 6 by 4.5 or 4 by 3, which is 1.33. That is a two-way slab, okay? So using table 27, alpha x value will be 0.0948 using interpolation, and because we have to only find out in the shorter span, so no need of calculating alpha y. Okay, so mx will be alpha x w lx square. Okay, so it will be 0.0948 into 24 into your 4.5 square, so that comes to be 46.08 kilonewton meter. I think we have calculated in the last problem also. Okay, per unit meter width. Okay, so using this equation, mu equal to 0.87 Fy AST D into 1 minus AST Fy by BD FCK. So this is basically the lever arm jet. Okay, this portion. So they, using derivation, we have found that Z is equal to D into 1 minus 1 minus AST Fy by BD FCK. Okay, so putting all the values, we get AST value as 793.65 square millimeter. Okay, so this is matching with option A. So A is the correct option. Okay. Fifth question. A simply supported reinforced concrete slab of effective dimension 4.5 meter by 6 meter is carrying a uniformly distributed load of 16 kilonewton per meter square, inclusive of the dead load, live load, and floor finish. Assuming M25 and Fe415 and thickness of the slab being 200 millimeter and 20 millimeter covered, what is the required spacing of main reinforcements in the shoulder span given 12 diameter bars being used? Okay, will it be 300 the spacing? Okay, will it be 193.6 will it be 256.2 or will it be 142.5 millimeter? Okay, so yeah, so I feel the question is the same as the last problem. Okay, so yeah, question is same, like the values are same, only the what we have to find is different. So yeah, so with 12 bars in the tension, okay, so one area of 112 bar is 113.1 square. Okay, so spacing will be 1000 divided by number of bars. Okay, so area we found to be 793.65. Okay, so number of bars required will be 793.65 divided by 113.1. So it will be 1000 by 793.65 divided by 113.1, which is equal to 1000 into 113.1 by 793.65. Okay, that comes to be 142.5 millimeter. Okay, and this spacing should be less than 142.5 3 into D, that is 174, or which comes to be 522 and 300. So it should be less than 142.5, 522 and 300, which is basically 142.5 Okay, so the spacing of the bar should be 142.5 So D is the correct option. So as you can see, D is the correct option. Sixth question. To prevent cracking of the edges, the corners should be provided with A. Shear reinforcement, B. Tension reinforcement, C. Torsion reinforcement, D. Your compression reinforcement. So which should be the reinforcement provided in the corners to prevent cracking of the edges? Okay, so the correct option is C. Okay, torsion reinforcement should be provided. Okay, because your this cracking of the edges occurs because of the twisting. Okay, twisting of the corners. So to prevent this twist, it's very important to provide the torsion reinforcement, so that will help prevent the cracking of the edges. Okay, so C is the correct option. That is, we have to provide torsion reinforcement in the corners to prevent cracking at the edges. Okay. Seventh question. Consider the following statements in regard to the torsional reinforcements. Okay. 1. It shall consist of top and bottom reinforcement, each with layers of bars placed parallel to the sides of the slab and extending from the edges a minimum distance of 1/4 of the shoulder span. Second statement, the area of reinforcement in each of these four layers, okay, shall be 3/4 of the area required for the maximum midspan moment in the slab. Okay. Third statement, for a corner contained by edges over only one of which the slab is continuous, the area of reinforcement in each of these four layers shall be 3/8 of the area required for the maximum midspan moment in the slab. And fourth statement, torsion reinforcements need not be provided at any corner contained by edges over both of which the slab is continuous. Okay. So which of the above statements is or are incorrect? A1 only, B2 and 3, C4 only, or D none. Okay. So if you check the IS code, okay, in the I think annexure D or E, something like that. Yeah, annexure D. So annexure D clause 8, D 1.8 to D 1.10. Okay, from IS 456 2000. So if you check that, you will find that these three statements are correct. That is, torsion reinforcements need not be provided at any corner contained by edges over both of which the slab is continuous. So torsion reinforcements need not be provided. So this is correct. For a corner contained by edges over only one of which the slab is continuous, the area of reinforcement in each of these four layers shall be 3/8 of the area required for the maximum midspan moment in the slab. So this is also correct if one edge is continuous. So we have to provide 3/8 of the area. Okay, reinforcement of the area provided for maximum mid-span moment. Okay. Second statement, that is the area of reinforcement in each of these four layers shall be 3/4 of the area required for the maximum mid-span moment in the slab. So that is also correct. Okay. However, in this case, it shall consist of 10 top and bottom reinforcement, each with layers of bars placed parallel to the sides of the slab. Okay. And yeah, and extending from the edges a minimum distance of 1/5, okay, of the shorter span, not 1/4. Okay, so it should be 1/5. Okay, so it should consist of top and bottom reinforcement, each with layers of bars placed parallel to the sides of the slab and extending from the edges a minimum distance of 1/5 of the shorter span. Okay, so that is incorrect. Okay, so A, one only is the right option. Okay, so that is 1/5. Okay. So as you can see, A, one only is the correct option. Okay. Eighth question. Okay, so this is related question now from the last question. So if area of steel reinforcement corresponding to the maximum midspan moment is 500 millimeter square, calculate the area required for the corner reinforcement for each layer if the slab is simply supported on both edges and meeting at the corner. Okay. So how much it should be? What should be the area of required, okay, for the corner reinforcement at each layer? Should it be 172.5 millimeter square? Should it be 250 millimeter square? Should it be 375 mm square, or should it be 500 mm square? So if you see here, the area of reinforcement in each of these four layers shall be 3/4 of the this one area required for the maximum midspan moment in the slab. Okay, so it should be 3/4. Okay, so here it is 500, right? So 3/4 will be 375 millimeter square. So required area for corner reinforcement is 375 millimeter square. That is C. Okay, so as you can see, C is the correct option. Okay, ninth question. uh, for a factored load of 15 kilonewton per meter square, inclusive of self weight on an interior panel of 4.2 meter by 6.25 meter, which are the effective dimensions. Okay, consider the following statements. One, the negative moment at the continuous edge for longer span rounded to two decimal places will be 18.75 kilonewton meter. 2. The positive moment at the midspan for longer span rounded to two decimal places will be 14.06 kilonewton meter. 3. The negative moment at the continuous edge for shorter span rounded to two decimal places will be 13.97 kilonewton meter. And 4. The positive moment at the midspan for shorter span rounded to two decimal places will be 10.78 kilonewton meter. Okay, so which of the above statements are incorrect? A, 1 only, B, 3 only, C, 1 and 2, D, 3 and 4. So let us check this. Let us solve this. So design load is factored design load is 1.5, sorry, 15. So we don't have to multiply by 1.5. It is factored load. So this is 15 and it is inclusive of self weight. Okay, so it is okay. This is an interior panel, so it will be, I think, the for from table 26 it will be the first case. Okay, case 1 out of the 9 cases. Okay, and ly by lx value will be, lx will be 4.2, always the lesser value lx, and ly will be 6.25, right? So ly by lx will be 6.25 by 4.2. Okay, so it is 1.488, which is two-way slab. Okay, so, as I told you from table 26, the first clause, okay, IS 456 to 2000, for longer span, okay, negative moment at the continuous edge, okay, yeah. So, from the table you will see that for longer span, negative moment at the continuous edge, alpha y value will be 0.032, okay, W is the 15, Lx is sorry, ly is 6.25. Okay, but we need lx, okay, because it is my is alpha y w lx square and mx is alpha x w lx square. Okay, so lx is only required, not ly. So lx is 4.2, w is 15. Okay, so alpha y is 0.032, so my is 0.032 into 15 into 4.2 square, which is 8.47 kilonewton meter, okay, per unit meter width. So here, yeah, so it is 18.75, but it should be 8.47. So one is incorrect, okay, one is wrong. So yeah, so it should be either A or C. Okay, B and D are not the options. Okay, So second statement, positive moment at the midspan. Okay, so that will be, yeah, so that will be basically the sagging moment coefficient. Okay, so that will be uh, yeah, so this should be alpha x. Okay, so it has been wrongly mentioned, written here. So this should be alpha x. So alpha x is 0.024. Okay, so and this should be also mx. Okay, not my. So it should be mx. So mx will be 0.024 into 15 into 4.2 square, which is 6.35 kilonewton meter. Okay, so yeah, so it is 6.35, but here it is written 14.06. Okay, so this is also wrong. So 2 is also incorrect. So 1 and 2 both are incorrect. So C will be the correct option. Okay. So let us see the other cases also. For shorter span, okay. So for shorter span, Lx will be again 4.2 only. Only alpha x values will change. Okay. So yeah. So negative moment at the uh, your okay, so I think this will be alpha y only. Only the negative moment for and positive moment the values will change, and similarly this will be my only because it is longer span. Okay, so it is right only. I only took it, I took it mistakenly. Okay, so it will not be mx. Okay, both will be my and alpha y. Okay, only the values will change. For shorter span, both will be alpha x and mx. Okay, so I hope it is corrected. So yeah, so negative moment at the continuous edge, as per the table, it will be alpha x is 0.0528. Okay, so as per this table, okay, table 26. So mx will be 0.0528 into 15 into 4.2 square, which is 13.97 kilonewton meter. So yeah, so negative moment at the continuous edge, okay, for shorter span, right? Rounded to two decimal places is 13.97 kilonewton meter. So 3 is correct. Okay, and positive moment at the midspan, for that alpha x will be 0.0408. So mx will be 0.0408 into 15 into 4.2 square, which is 10.78 kilonewton meter. So if you see, the positive moment at the midspan for shorter span rounded to two decimal places will be 10.78 kilonewton meter. Okay, so that is the value which we have, they have also found. So it is correct. 4 is also correct. So 1 and 2 is incorrect. So C is the correct option, as I told you. So as you can see, C is the correct option. Okay, and last question. Okay, 10, an interior panel of 4.2 meter by 6.25 meter effective dimensions subjected to a factored load of 15 kilonewton per meter square. So is it the same question? Yeah, almost the same question plus additional data they have given. So yeah, so panel is having this dimension and factored load of 15 kilonewton per meter square inclusive of cell weight. The slab is provided with main reinforcement bar diameters 8 mm and has a thickness of 150 mm. Clear cover is 20 mm. Grade of concrete is M20. Grade of steel is Fe415. Okay. So consider the following statements. 1. The section is over reinforced. 2. The maximum shear force is equal to 15 kilonewton. 3. To resist the negative moment at the continuous edge for shorter span, the minimum area of steel shall not be less than 324.41 millimeter square. 4. The spacing of main reinforcements shall not be more than 300 millimeter. Which of the above statements are correct? A 3 only, B 2 and 3, C none, D all. Okay, so let us see this. Let us solve this. So shear, factored shear, it will be how much? WU into LX by 2. Okay, in the shorter span. So yeah, so it will be 15 into 4.2. Okay, divided by 2. Okay, so that comes to be 31.5 kilonewton. So yeah, so if in the shorter span only it is coming 31.5, in longer span which will have a value L of Ly which is greater than 4.2 6.25, it will be definitely higher than 31.5 and it will not be 15. Okay, so second option is incorrect. Okay, then second point. So yeah, so we need to find the based on this, for seeing this reinforcement whether this section is over or under reinforced. So we have found from last question that the maximum moment is how much? 13.97, right? So 13.97 is the maximum moment, and Fe415 is the steel. So limiting condition is Mu equal to 0.13 FCK BD square, right? B is 1000, FCK is yeah 20. So solving we get D required is 71.15 millimeter. Okay, that is D required. But we have provided 126 millimeter, right? So definitely Definitely we have provided more concrete depth, so it will be definitely be your this one under reinforced. Okay, so it is safe also and under reinforcement, and it is reinforced on, that is an ideal design. Okay, we should always design for under reinforced. Okay, because the failure is uh, this one not sudden. Okay, so it is progressive and it will show. Okay, it will be visible and it is long term. Okay, not a sudden brittle failure. So yeah, so it will be under reinforced. So the first, the section is over reinforced statement is wrong. It will be under reinforcement. So yeah, so 1 and 2 both are not correct. So D will not be the option. B will also not be the option. Okay, it will be between A and C. Okay. Third statement. Yeah, so area of steel. Okay, minimum area of steel we have to find at the negative moment at the continuous edge for shorter span. So let us see. So for that case, negative moment at shorter span, right? So shorter span negative moment, that is 13.97 itself. So 13.97 using this formula, right? Mu equal to 0.87 into Fy into AST into D into 1 minus AST Fy by FCK BD, right? So Mu is 13.97, Fy is 415, AST we need to find. D is how much? This one 126, right? Sorry, yeah, 126. And AST find, we need to find Fy is 415, right? Yeah, FCK is 20, yeah, and B is 1000 and D is again 126, right? So solving we get AST is 324.41 millimeter square. So to resist the negative movement at a continuous edge for shorter span, the minimum area of steel shall not be less than 324.41 mm square, right? So 3 is correct. Okay, statement 3 is correct. So yeah, so all are not correct. 2 and 3 are also not correct, and there is at least one option correct. So none will also not be the option. Okay, so this is not the option, this is not the option, this is not the option. So 3 only is the correct option. Okay, so this is the correct choice. So for that to happen, 4 should also not be correct. Okay, so let us see that also. So they have provided 8 bars, right? So 8 bars for spacing, which will be the amount of spacing required will be 1000 divided by 324.41 divided by pi by 4 into h square, which is 50, I guess. Yeah, 50. So 50.3. So this comes to be 155 millimeter. Okay, and 3 times the so spacing will be minimum of 155, 3 into effective depth, and 300 okay, so 3 times effective depth is 3 into 126, right? So that is 378 so it should be minimum of 155, 378 and 300, so which is 155 okay. So hence the spacing of main reinforcements shall not be more than 155 okay, but here it is given as it should not be more than 300 so this is wrong. Okay, so it should be not more than 155 okay. So fourth option is also incorrect as we predicted. Okay, so the correct option is 3 only. Okay, so A is the correct option. So as you can see, A is the correct option. Okay, 3 only. So yeah, so with this we come to end of today's lecture. So it has finished little faster because of lesser correspondence. So I think from coming classes we will next class onwards I think we will start columns. Okay, column design of columns and all. And also I would request you to at least solve all the problems that we have discussed in examples as well as the solve problem section, so that you are well versed with the topic and you have understood in depth. Okay, how to design. Okay, so it will be very easy for you to apply in real life also, and it will enhance your understanding of the subject matter, right? So yeah, so I wish and also request you to please solve all the problems at least once. Okay, so with this I would like to end today's lecture. Okay, let us meet next week, and till then wish you a happy coming week. Okay, so hope that you try to learn the coming lectures, and we will discuss it in the next class. Okay, so with this I would like to end today's class. Okay, have a great day. Okay, bye.